Have you ever wondered how a computer, a machine that runs on pure logic, can possibly deal with all the chaos and randomness of the real world? Well, today we're going to pull back the curtain on the mathematical secret that makes it all happen. We're talking about random variables. I mean, just think about it. From totally random spikes in website traffic to the complex, almost unpredictable behavior of an algorithm, our digital world is just full of randomness. So, how do we get our code to not just cope with this mess, but to actually make sense of it? And look at this, we're talking about building a secure password, trying to predict stock market trends, or even something as basic as sorting a list of names. They all share one single common challenge: dealing with the unknown. And believe it or not, they all use the exact same clever solution.
So what is this powerful, super elegant tool? It's something called a random variable. But I gotta tell you, the name is a little misleading. So let's break down what it really is, because it's not what you think.
This quote right here absolutely nails it. A random variable isn't really random, and it's not a variable like an algebra. Nope, it's way more like a translator. Its entire job is to take real-world events, messy, chaotic events, and turn them into clean, simple numbers that we can actually work with. Okay, here's the formal textbook definition. That capital X, that's our random variable. It takes an input from S, which is the sample space. That's just a fancy term for all the possible things that could happen. And it maps it to R, the set of real numbers. See? It's literally a bridge from the real world to the world of math. Let's see this in action with a super simple coin toss. We flip two coins. That gives us four possible outcomes, right? Heads, 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 tails, and so on. Now, we define our random variable, x, as the number of heads. So heads, heads gets translated to the number 2. Heads, tails, and tails, heads both become 1, and tails, tails, that's a 0. And just like that, we've translated a random event into a neat little set of numbers. Simple enough, right? Okay, so these translators, these random variables, they come in two main flavors, and knowing the difference is absolutely crucial for how we analyze them. So, on one side, you have discrete random variables. This is where you can actually count the possible outcomes. You know, like the number of heads in a coin toss, or the number you get when you roll a die. It's 1, 2, 3, 4, 5, or 6. That's it. But on the other side, you've got continuous random variables, and these can take any value within a range. Think height, weight, or temperature. You can't just list out every possible temperature, right? Because between 70 and 71 degrees, there are literally infinite possibilities. Now, for discrete variables, we can build a simple table like this one. It's called a probability mass function, or PMF for short. Think of it like a complete instruction manual for our random variable. It lists every single numerical value it can possibly take and the exact probability of that value happening. And here's the key. All those probabilities have to add up to 1, to 100%. Okay, so we've successfully translated our random outcomes into numbers and their probabilities. Now for the really cool part. What can we actually do with them? Well, we can start calculating some incredibly useful things. The first, and probably the most common, is the mean, which is also called the expected value. Now, that formula might look a little intimidating, but all it's saying is this. Take each possible value, multiply it by its probability, and then just add all those little pieces together. What you get is the average outcome you'd expect if you ran the experiment over and over and over again, like an infinite number of times. So, you remember that table from a moment ago? If we just plug those numbers into our formula, we get an expected value of 2.9. It's a simple calculation, but what it tells us is incredibly powerful. So here's the million-dollar question. What does that number even mean? The variable can only be 1, 2, 3, or 4. It can't actually be 2.9. Well, what it tells us is its long-term average. It gives us a center of gravity, a point of prediction in a process that is fundamentally random. And that is unbelievably powerful. But you know, the mean isn't the whole story. We also need to know how spread out the results are. Are they all clustered super tightly around that 2.9, or are they all over the place? That's what variance tells us. This idea of spread is so important. In finance, a high variance means high risk. In networking, it could mean an unstable system. It's not just about the average, it's about how predictable things are. Which, of course, brings us full circle. We started with a big problem. How does code handle unpredictability? We found the solution, the random variable as our translator. So now let's see exactly how this gets put to work in the real world of computer science. And this is where it all comes together. In machine learning, random variables let us understand and actually quantify the uncertainty in our predictions. In networking, they help us model traffic so our systems don't crash. And in cybersecurity, they're literally the foundation for creating encryption keys that are impossible to crack. It's all about using this mathematical framework to bring predictable order to completely unpredictable systems. So the next time you check a weather forecast or see a stock market prediction, just remember the humble random variable working its magic behind the scenes. It's the tool that lets us find the signal in all the noise. And that leaves us with a pretty fascinating question, doesn't it? What other unpredictable parts of our world could we understand better if we just found the right way to translate them into numbers?